Hello and welcome to seminar number 14. Today we are going to talk about hydrogen and its isotopes. So, what's the plan for today? Differences due to nuclear properties, differences due to masses, isotope effects, how to make deuterium, why to make deuterium, and a fancy treat at the end of the presentation. So, isotopes. Isotopes meaning same proton number, different neutron number. For example, we have 1H, 2H or 3H, meaning that we have one nucleon inside of the hydrogen atom, which is in this case just one proton. In the 2H isotope, we have one additional neutron, so therefore the neutron number changes from 0 to 1. And then we have another isotope with two neutrons. These have special names. They are called protium, deuterium and tritium. I'm not going to use the name protium, I will just stick to hydrogen. But this is not the case for every isotope. So if you look at calcium-40 and calcium-41, the calcium-41 isotope will not have a special name, it will just be called calcium-41. There are certain exceptions, for example, thorium-230 has its own name. This is called ionium, for example. But this is not the case for every isotope. So let's go into the first real topic for today. Differences due to nuclear properties. So isotopes have different nuclear properties because the hydrogen atom contains just one proton and one proton in the nucleus, meaning that the hydrogen has a nuclear spin of +1/2. Deuterium, on the other hand, has one additional neutron, and this one neutron has also a spin of +1/2, meaning that the deuterium nucleus has a nuclear spin of +1. This is interesting because we differentiate between different hydrogen molecules. So if you have an H2 molecule, there could be that both spins of both hydrogen atoms are aligned, meaning they form the ortho hydrogen, or they are, opposite of each other, and this is called parahydrogen. For example, if we now take a look at hydrogen, the 1H H2 molecule has a spin of +1. If we have a D2 molecule as orthohydrogen, this would then have a spin of +2. Of course, the parahydrogen both are ±0. And at room temperature, this difference due to nuclear spin properties becomes apparent as the ortho-para ratio for H2 is 3:1 and for deuterium it is 2:1. This is fancy physicist stuff, but chemists don't usually care about that. I just wanted to have that mentioned. So, let's come into isotope effects. Isotope effects meaning that they have different chemical properties because most chemical reactions rely on movement of atoms. And of course, if you have a heavy atom, this will move a bit slower than the lighter atom. For example, if you look at the carbon isotope, carbon 14, 13 and 12, we can see that the carbon 14 to carbon 12 bond is stronger than the carbon 12 to carbon 12 bond. This means that some of them react slower. For example, if you look at carbon 14 labeled malonic acid and then decarboxylate this malonic acid, you can then see that the carbon 14 to carbon 12 ratio is 1.06. Whereas if you use carbon 13, the ratio of carbon 12 to carbon 13 would be 1.03. This means that the CO2 from the decomposition of malonic acid is relatively heavier isotope depleted. Sometimes you will have the opposite effect. For example, heavier isotopes prefer to stay in the compound with higher heat of formation, which in the first example would be the CO2. But for example, if we look at deuterium from H2 and have a equilibrium between H2 and H2O, if one of these H atoms would be a deuterium, the deuterium from a, for example, D2 molecule into H2O would move into the H2O molecule forming HDO. This is also the same case for nitrogen 15. So if you have a equilibrium of ammonia and the ammonium ion, the N15 isotope would prefer to stay in the ammonium ion as this is the compound with higher heat of formation. And now on to how to enrich for deuterium. Deuterium acts temperature dependent, meaning that at higher temperature the deuterium prefers to stay as hydrogen sulfide, and at low temperatures it prefers to stay in the water. This is the equilibrium that we are looking at. For example, if we have just normal H2O and then deuterium containing hydrogen sulfide, we can switch the deuterium from each compound depending on the temperature. This is done via the Girdler sulfide process. I kind of have an issue with this labeling, but let's say, for example, if you have normal water with natural deuterium levels, in this high temperature stage, the normal deuterium from normal water content would then move into the hydrogen sulfide. This hydrogen sulfide will then be enriched and can then, at the low temperature stage, exchange its newly gained deuterium to the hydrogen, and then you can have enriched water and so on until you reach an enrichment grade of 12%. If we want to go a bit higher, we will use electrolysis because protium or hydrogen normally is reduced electrochemically a bit faster than deuterium. And if we want to get into this really highly enriched deuterium or heavy water, you would use distillation. As you can see here, depleted water from the hot water output. So normal water, relatively depleted water, and then you have relatively enriched hydrogen sulfide. And this relatively enriched hydrogen sulfide can then move into the low temperature stage where it gives its newly gained deuterium to the water, and this water will then be comparatively enriched. And then you can use this enriched water and so on up to 12%. Why do you need deuterium or heavy water? Deuterium as D2O, so heavy water, is a polar solvent in NMR analysis. So when you do NMR analysis, you mostly measure H1 and carbon-13 NMR from your organic molecule. And if you had some H1 from regular water, which you would use for dissolving your compound, this would dwarf any signals of your H1 of the molecule that you are trying to measure. So you would want to have the solvent as free of just normal H1, so therefore you can then measure only the H1 from the molecule that you are actually trying to analyze. And of course, since we are talking about nuclear stuff, deuterium oxide or heavy water is used as a moderator for low enriched fuels because deuterium has a very low neutron capture cross-section and allows for a high neutron flux even at low enrichment grades of just natural levels. So you kind of have to at least enrich one isotope. If it's not the uranium-235, you would have to enrich for deuterium. And another not so pleasant example is the hydrogen bomb. So in the hydrogen bomb, you basically have an atom bomb with fusion, and you would want to fuse deuterium or tritium, since tritium is not really an option because it's really expensive and you can't store that well. You would use deuterium, and the compound lithium deuteride is a solid at room temperature, meaning that you would have a crystal structure where all the deuterium atoms are already very close together, meaning that it's much easier for them to fuse together, and therefore you would use lithium deuteride. This is lithium hydride. It's quite an interesting compound because it contains the H- ion, which I find quite interesting. Also, you would use it in synthesis of deuterium-labeled molecules, but I'm not an organic chemist, so of course there are other applications for deuterium, but here are some important ones. Coming to other differences, deuterium, tritium, and just normal hydrogen. As you can see here, they have different boiling points, which I want to see that experiment where you determine the boiling point of just normal tritium gas, which is absolutely insane. And here you can see the differences of just normal water and heavy water. And as you can see, the densities are different. And there's a really famous example on YouTube where someone puts in a heavy water ice cube and it sinks in just liquid water because the density of deuterium oxide is higher than the density of just normal water. But this is quite an expensive experience. As you can see here, deuterium oxide costs around 2,300 euros per liter. So a really expensive experiment. But you need it for example, NMR analysis. And last but not least, the fancy stuff, H7. We were talking about the first hydrogen isotopes, but there are many more. For example, the heaviest one is the H7. How do you even get H7? This has no fancy name, just to say that. It's bombarding just normal hydrogen with a stream of helium-8. Helium-8 is also really... Normally you have helium-4, right? And helium-8 is really something neutron-rich. And in a very unlikely case, the helium-8 gives all of its 6 neutrons to the protium, creating H7. And this is only possible at the Riken's radioactive isotope beam factory, because the helium-8 stream, that's not something that you just have in a normal nuclear lab. With that being said, thank you for your attention and goodbye.